2.8 Hanging chain. A chain with uniform mass density per unit length hangs between two given points on two walls. Find the general shape of the chain. Aside from an arbitrary additive constant, the function describing the shape should contain one unknown constant. The shape of a hanging chain is known as a catenary. The unknown constant in your answer is dependent on the horizontal distance d between the walls, the vertical distance lambda between the support points, and the length L of the chain. Figure 2.14. Find an equation involving these given quantities that determines the unknown constant. So the first thing that most people notice is that it has 4 stars, which is the highest level of complexity or difficulty in a Moore and Redbrook problem. So let's first have a strategy on how to tackle this problem. So first we're going to analyze a small chunk of the chain and then look at what forces are acting on it and then build y of x from that using integration. So now we can look at the actual figure 2.13, and just look at all the forces that were going to be on it. So first we're going to have the weight, and then we're going to have the tension, which goes both ways, as you can see from the 2 arrows. And now let's look at what we can do with that. So the biggest part of this is actually how many relationships can you get from all of these? How many things can you relate together? So let's look at one part that we can relate, which is the statics. So that means that the net forces in the y direction have to be 0 and the net forces in the x direction have to be 0. So now given that, let's analyze the small chunk that we said that we would do in our strategy. So we have our small length of the chain, and this is going to be ds, which is going to be that small arc length that we're going to have. And this is because this is going to be curved. So now we have at the endpoints, we have tx, and then we have tx plus dx. So we have a small change of dx in the tension, and we also have our weight force, which is going to be rho dsg, which we get from the density constant as it has a uniform density. So now we'll use one part of our statics requirements, which is that the forces in the x direction have to sum up to 0. So this is going to be only tx, and from that we know that tx must balance each other, so that means that it has to be constant. So in other words, we can write that tx equals c. So now we have one relation, and now let's look about how we can relate this tx to other places. So now we're going to just zoom in on our tiny part of the chain. We'll have ty, tx, and then y prime, which is going to be our slope. So now we know that y prime is just going to be ty over tx, and we can use that tx equals c to get that cy prime is equal to ty. And now what we can do is analyze the forces in the fy direction now. This is a crucial step right now because we basically have what the function is in terms of its derivative and fy. So the 2 forces we have are the weight force and the tension, and because of statics, we know that the net forces of this fy direction have to be 0. So the weight force and the tension need to balance each other out. And what we can see from our diagram is that the difference in the tension, the difference between the right and the left, are actually what is going to balance with the weight force. So now we have another relationship. So this is dty is equal to rho g ds. And now let's look at how we can make ds in terms of things that we know, which is dx and dy. So now if we have a tiny segment, which we already know we have, we can just think of this as a triangle. Using Pythagorean theorem, we have this, and we can isolate for ds. So now what we're going to do is take the dx out of it for the specific reason of getting dy over dx. We know that dy over dx is y prime. And that is useful because we already have that in another relationship, right? So now we can substitute ds in for our things with relation to y prime. We also have that cy prime is equal to ty, so now we basically have everything in terms of some sort of y. So now all of this is just going to be integration and just math. So now we're going to have y of x equals 1 over x, hyperbolic cosine of dx plus a, and then plus b. However, a plus b are just phase shift constants, so we're just going to set those equal to 0, which we can because it just depends how you define y and x equals 0. So now we just have y of x equals 1 over d, hyperbolic cosine of dx. So now we're going to build off of that and actually try to find our rho g over c, or our d. So as you can see in the figure, what we have is a d that separates the horizontal distance, and because of that, we're just going to change our d, which equals rho g over c, to just alpha. So now a big part of this is actually you cannot assume that this system is going to be symmetric. Even though we have a distance d apart, our difference in height actually makes it so that the lowest point is not required to be at the center. And because of this, we're just going to relabel our points and redefine them just so it's easier to look at. So we're going to have our 0 at the lowest point. This is an arbitrary distance. We don't know how far it is. And then we're going to have our left endpoint be negative x0, and then we're going to have our right endpoint be d minus x0. So from part A, we already have what our height is as a function of the x. So we have y of x, right? So now what we can do is define our lambda. Our lambda is the change of the height from our right endpoint to our left endpoint. So what we can do is plug that in. So now we have lambda in terms of our y of x function. So now what we're going to do is we're going to plug that into our known function, which we found in part A. And all we're doing is making it simpler in terms of alpha lambda. So now we're going to do the same thing for L. We're just going to try to find it in terms of our y of x function. And we already know from part A, this is just going to be the integral of our ds. So now we already know what ds is from our part A, and now we can just plug in what we already know for y prime. And the other thing is we need the bounds, which is just going to be our left endpoint and then our right endpoint, and we defined that previously, so that's just going to be negative x0 to d minus x0. So now we're just going to plug this in, and then we get that in terms of alpha L. So now let's look at these two, and you see we have similar things in this. So we're just going to label these as A and B. So we have A equals d minus x0 times alpha, and then we have B is equal to negative alpha x0. So now we're just going to rewrite these as their simpler terms. And now if you see where this is going, we're just trying to find a relationship by using this system of equations. So now what we're going to try to do is just put these into one equation. So after simplifying using known identities, we're left with this equation, but keep in mind we don't want to leave it in terms of A and B because those are things that we defined, right? So now we can actually just find A and B, which simplifies the equation to this.